this is a very fast car. But how fast? I guess what you could do is you could, as it's going, you could do a frames per second analysis versus the 1 centimeter ruler behind it, and that would certainly do it. One other way of doing it might be to get some sort of gating system going so that, let's say you had the car here and you had maybe a light source on this side and you had some sort of detector on the other side. Maybe this was hooked up to some sort of AVR, maybe an Arduino, and then you had another light source at the end of a run of a known distance. Let's say it's something like 20 meters. And then you have, under here, you have another collector of light, and that also was somehow processed by the Arduino. What you could do is you could use these like, I guess they're gates, aren't they? So this starts off with where this is on, it's triggered, and then as it goes through to the other end, this is on and it's triggered at the other end. Measure the time here, millis, measure the time at the other end, millis, do the subtraction, divide it, do the time. I guess you could work out the speed as well based on this, but just the time itself would be enough. So that was the task that came to me via a STEM club at school, where they wanted to know, because they've been timing it by hand, and down to the millisecond, that's quite difficult to get the timing at the start and the finish. The cars themselves are a little larger than this, and they are gas-powered in that they have those little carbon dioxide cylinders attached to them. And the students spend a lot of time doing the design work so that this thing gets to the other end as quickly as possible. There is a wire from one end to the other, so they are guided. And then my job was to just think about how could I actually design this so that it worked? So my first thing to do was to try and put together some code on an Arduino and one light gate acting as both start and finish, so I could see if it was, proof of the process itself. And then from there, maybe we could extend it out to, like a much larger playing field. So let's have a look at that. So we have our prototype set up here, and originally I was thinking of a laser shining onto, this is a photodiode, and then the photodiode is hooked up with a voltage, in a voltage divider configuration. This is a 10K resistor here, and then that feeds back to A0 on the Arduino. And then the code simply does all the little definitions. Now I've actually even got here the start pin and the stop pin ready to go, but I won't be implementing the stop pin just yet. The thing is, there's a lot of different ways of doing this. I've tried to keep this fairly simple because I want to hand over the code to the students to tamper with. So at the moment, for instance, there's nothing in here about interrupts, whereas that's probably how I would go. There's my timing. Oh, I've got a sensor value which picks up, that's your direct reading from your analog input. And then actually an output value is, I've actually just mapped it 0 to 100 like a percentage. There's our timing, so the go time, the stop time, and the difference between them. And then I've actually converted that to a print time. Yeah, don't show that message again. What's that about? I've actually converted that to a print time. And that's as a float, and that means you get the precision to 3 decimal places, which is what I want. There's an ambient setting here for the light, which I've set at 50, but in fact you could set it anything between 0 and 100, and you could also swap out this 10K resistor for a 10K pot, for instance. So that would be your adjustment for the sensitivity of the voltage divider here, and thus the light at which this is triggered. Then we've just got some setup stuff, so it just says, yep, let's go racing. There's a bit of a delay to start with to make sure everything settles down, and you could change that as you see fit. Then you do a reading, you map it from 0 to 100, and then you say, okay, so if it's greater than ambient, now when this has got light on it, the photodiode outputs around about 0 on that percentage scale, and then when you cut that light, it shoots up to about 50 or 60. I mean, a lot depends on the conditions, but basically that's what's happening. So if it goes above that ambient value, then it says, right, let's go, print go, delay 500. And what that does is that when the car goes through, we don't want the back end of it to trigger it. So it gives it plenty of time for the car to go through. Then it says, okay, so let's do another reading. Now this would be at the other end. So when I hand this code over to the students, this would be not the start pin, but the stop pin. But anyway, go with me on this one. So then we do the conversion, and then we say, okay, while the output is less than ambient, in other words, it hasn't been triggered again, just keep taking readings as you go. Finally, when it does trigger, stop, find out what the stop time is, do the subtraction, and then print everything out. Wait 5 seconds and start the whole shebang again. That's what should happen. So first thing I want to do is get it uploaded to the Arduino. So let's do that. So that's compiling and uploading is good. And then we want to go to the serial monitor. And let's just get this over here a little bit. And it says, okay, so it's triggering pretty early actually. So yeah, we might put some more light on it maybe. Let's see how we go with a little bit more light on it. And let's just see what's happening. So no, that's good. So we'll just trigger it to stop. Yeah, there we go. Okay, so that was an ambient light thing, and the easiest thing to do was just for me to turn the lights on. So it's racing and ready to go. I'll trigger it. Where's the car? I mean, we should do this properly, shouldn't we? Here's the car. So the car triggers it at the start, and you can see it says go. And then a number of seconds later, I don't know, 5 seconds later or whatever, it triggers it again at the other end. And that's stop. And what is that? 8.135 seconds. Let's go again and have a shorter one. And that's 2.727 seconds. So yeah, I think that's proof of concept. Now I'd like to do more with this. I mean, one of the things is that I have been told is that we can't use lasers with the kiddies because they might poke their eyes out with them. So I might just set this up again with something like a torch. I was actually thinking, I found these little straw hat LEDs, these little guys, and they're quite good. So I might actually put one of these in a tube and fire it up there. Let's do that and see if we can't get a similar sort of result. But I'd say that's proof of concept. I can hand this over to the students. They can do the final development and final code development. They can get their second gate working now that I've showed them how to do the first gate. Should be good. All right, so let's reset the guy without disturbing it too much. So this will be, yeah, look, obviously this is going to be a bit of a wider gap. And yeah, actually a co-conspirator of mine came up with the idea of putting a tube around the LED, like a glass tube, and then wrapping that glass tube in aluminium foil with a shiny side in, and that should direct it a lot more to here. You can always change the nature of this LED. I might even try it with a torch actually to see if that works as well. But in the end, all you need is a change of that ambient light measurement, or rather the fact that gap has been breached. So if we just try that, and yep, that's a go. And then a few seconds later, interruption, 4.36 seconds. That's pretty good. Proof of concept. I'm pretty happy with that. That's the circuit working for this week. See you next time.